All right, so last time we developed some of our basic antiderivative rules. So essentially all the rules that you know from derivatives, those that can be quickly, simply, easily applied in reverse, essentially. A couple other ones are that you can take an antiderivative term by term. So the antiderivative of a sum or a difference is the sum or difference of the antiderivatives, and a constant multiple will get carried along. So let's take a look at some examples here. So suppose we start with this one. So we're going to be finding the antiderivative. And sorry for the notation, we will develop different notation later, but essentially we start with a lowercase function and we'll denote the antiderivative with the capital letter. So it's just standard practice here. So suppose we have lowercase f is equal to negative 4 square root of x plus 3 over x squared plus 7e to the x minus 3. All right, so this is one that I would say is not quite ready to take its antiderivative yet. We need those x's to powers, and they need to be in the numerators. So we have the first term we really need to rewrite as the rational exponent x to the 1/2 power. Also, the second term, we need to rewrite this as x to the negative second. We do not have and we will not have a quotient rule. So we need to rewrite those denominators and bring them up into the numerator like that. All right, so with that, then now we are ready to take the antiderivative. So capital F of x is going to equal, constant multiples get carried along, and now it is the power rule where we add 1. So 1/2 plus 1 would be 1 1/2, or 3/2. So let's go ahead and just write that as the 3/2 power, and then divided by that 3/2, which we are going to bring up as multiplication by the reciprocal. And then x to the, again, we are adding 1. So negative 2 plus 1 is to the negative first power, and then divided by that power. So it'll take a little while before this becomes, natural. You've spent most of the semester doing the exact opposite, so it'll take a little bit. And then plus 7e to the x, and then the antiderivative of a constant is that constant times x, and then always plus an arbitrary constant c. All right, in this first term, I don't want to see complex fractions. So dividing by 3/2, you should be able to rewrite that and realize that is like multiplying by the reciprocal of 2/3. And so this is going to mean your first term, when you multiply it by the negative 4, is going to become negative 8/3. So negative 8/3 x to the 3/2. The second term we could rewrite as minus 3 over x. And then just the last two terms here, and then plus our arbitrary constant. All right, so there is our antiderivative. Now remember, you could always check these answers by taking their derivatives. Now I won't always be showing these checks, but you always have the ability to do so. So if I bring down the 3/2 power, and I was just going to now take the derivative, so I am taking, when I do my check, I'm taking capital F prime. So the 3's would reduce, and the 8 divided by 2 would give me negative 4. X to the 3/2 minus 1 would be 1/2. And then the derivative of minus 3 x to the negative 1. So the negative 1 would come down, times the negative 3 would be plus 3. X to the negative 1 minus 1 would be to the negative second. Plus 7, derivative of e to the x is e to the x. Derivative of minus 3x is minus 3, and the derivative of a constant would go to 0. So we always have the ability, even if we don't always show these, to run these checks. All right, let's look at another example. So number 2. Okay, so suppose we have little f here, lowercase f is equal to cotangent x times sine of x. Now, the first thing I want you to kind of think about here is, even if you knew the antiderivative of cotan, which you do not, we don't know a function whose derivative is cotangent. But even if we did, we do not have a product rule. So you cannot take an antiderivative factor by factor. So what this means is we're going to try to, in a case with trig functions, maybe do some trig identities and get this in a form that we can take the antiderivative. So of course in this case, cotangent is equivalent to cosine of x over sine of x. And then when we multiply that by sine of x, this original function really just simplifies to cosine. And so that will mean that its antiderivative, capital F of x, is sine of x plus c. Okay, so it's going to take a while to just kind of get into our heads that we're doing the opposite, right? And we're not in a situation where we're going to have a product rule or a quotient rule. So sometimes with trig functions, maybe a little bit of simplifying will be necessary. All right, number 3, suppose you were given a product, something like x times the square root of x minus 3. Now, in the last example, we were given a product, but it was a product of trig functions, so of course we could just use basic quotient identities in order to simplify that to a form we could take its antiderivative. The most important thing to realize here, because it would be maybe a little more tempting here, is to realize it is not the case that the antiderivative of f, so capital F, is not just, oh, I'm going to do power rule. So x squared over 2 times x to the add 1 and divide by it, right? So 3 halves over 3 halves minus 3x. And so this is what you need to be really careful of here. Okay, so this is my caution. You cannot take a derivative factor by factor. You can't now, and there won't ever even be a product rule to allow you to take the antiderivative of a product in any other way. So here, even after we learn some other techniques later on in the next chapter, something like this is still going to always kind of require of us to simplify it first. So on this one, we are going to start by multiplying it out. So this one is not in a form yet that it's ready to take the antiderivative. But if I distribute, I would have x to the 3 halves minus 3x. And now it's ready to take the antiderivative term by term. So capital F is going to be x to the adding 1, 3 halves plus 2 halves would be 5 halves, divided by that 5 halves, minus 3x to the 1 plus 1 would be 2, divided by that 2, and then plus our arbitrary constant. So our antiderivative here, again cleaning up, dividing by 5 halves is like multiplying by 2/5. So 2/5 x to the 5 halves minus 3 halves x squared plus c. So if you have a product, you need to multiply it out. Or if it is a trig function, you might have to do some trig identity work before you can take the antiderivative. All right, so what if we had something like this? F of x is equal to, and suppose we had 4x to the third plus x squared minus 2x minus 3 all divided by x cubed. All right, so again, my caution. What you cannot do, we are not allowed to take the antiderivative of a quotient as the quotient of the antiderivatives. So this is not going to be, oh, good old power rules. So x to the 4th over 4 minus, I guess it's plus, x cubed over 3 minus 2x squared over 2 minus 3x all divided by x to the 4th over 4. Okay, you cannot take an antiderivative of either a quotient or a product, like in number 3, as the either product or the quotient of the antiderivative. So don't fall into that kind of error. So what is this going to mean? Well, much like in number 3, it meant first we had to multiply it out. In number 4, it's going to mean the first thing we want to do is to divide it out. And so if you just have a monomial in the denominator, like we do, you want to just think about dividing each term in the numerator by that denominator and simplifying. So in the first term, 4x cubed over x cubed is just going to be 4. In the second term, x squared over x cubed is going to be 1 over x. In the third term, minus 2x over x cubed is going to be 2 over x squared. And the last term is going to be minus 3 over x cubed. Now, we should probably think about rewriting these exponents, bringing them up into the numerator, like we did in our very first example, because again, we can't take the quotient of the antiderivatives. You can't just apply the power rule when it's in the form of a fraction like that. So we bring those up into the numerator. Okay, this is now in a form that is ready for its antiderivative. So capital F is going to be antiderivative of a constant is that constant times x. And on all of these next 3 terms, you should be thinking just power rule. Okay, so I'm going to start with the last term, and I'm going to say, all right, so power rule. Minus 3 gets carried along as a constant multiple. I'm going to add 1, so negative 3 plus 1 is going to be negative 2. Divided by that negative 2. And the previous term, minus 2 is a constant multiple, x to the negative 2 plus 1 is negative 1, divided by that negative 1. Now, here's the thing. Feels like this should be the exact same thing, plus x to the negative 1 plus 1, but this gives me x to the 0 divided by 0. This needs to be your red flag that something just went wrong. So remember, this is the one situation where you don't get to use power rule. So you kind of gonna go, oh yeah, that's one time, and you'll do it once or twice, and then you'll remember the antiderivative, and it might be easier to go back and look at it as this 1 over x instead of x to the negative 1. So the function we learned whose derivative is 1 over x is this natural log of, and then when we go in reverse, kind of that domain issue, we said we actually need it to be natural log of the absolute value of x. So here is our antiderivative. Capital F is equal to 4x plus natural log of the absolute value of x plus 2 over x plus 3 over 2x squared plus c. Now you could leave those negative exponents if you want, plus 2x to the negative first or something like that. But, you should get efficient, I think, at going back and forth between these different forms that you have here. All right, so let's just look at a couple more here. Number 5, so we want to hit quite a few of these different antiderivative rules that we have. So suppose that we have f of theta is equal to 3 theta. Oops, that does not look like a theta. 3 theta plus cosine of theta and plus cosecant squared of theta. All right, so let's take this antiderivative, and this is in a form that's ready because we know we can take the antiderivative term by term, and each of these are functions that we can find their antiderivatives. So the first term's just power rule, so 3 and then theta squared over 2. Now we want to think about, well, if the derivative of sine is cosine, then the antiderivative of cosine, that was equal to sine of theta. And then cosecant squared, so if you remember, the derivative of cotangent was negative cosecant squared, so the antiderivative of cosecant squared is negative cotangent of theta. And this might be a good time to, again, run a check, especially if you weren't 100% sure maybe about the trig functions or something. So let's take our f prime. So bringing down the 2 in the denominator with the 2 I'm bringing down would reduce, and it would just be 3 theta to the first. Derivative of sine is cosine, minus derivative of cotangent is negative cosecant squared, so that negative with this negative does take me back to the positive cosecant squared theta. And so maybe that little extra check the first time or two might be kind of reassuring there. So that would be our antiderivative. So right now with the trig functions, you have this very specific set of 6 functions that you know their derivatives. Now you know those antiderivatives in reverse. And it's not sine, cosine, tangent, cotangent, secant, cosecant. It's actually sine and cosine, yes, but then it's the secant squared, the cosecant squared, secant tangent, and cosecant cotangent. So those are the 6 you know from their derivatives. You now know those antiderivatives in reverse. All right, number 6. Suppose we have f of, let's say, u is equal to 4 over u squared plus 1 minus 3 to the u plus 7. All right, so the first term might be a little bit concerning because it's like this quotient, but hopefully this is one. Go back and look at your list if you're not sure. That's one that we learned the derivative of. 4 gets carried along as a constant multiple, but we learned that the derivative of tan inverse or arctan of u is 1 over u squared plus 1. So this is the antiderivative. And then the antiderivative of 3 to the u is going to be 1 over natural log of 3 times 3 to the u, and then plus 7u, and then plus our arbitrary constant. So again, if there are ones that you're not as familiar with, run that check. If you're not sure, you're feeling uncomfortable, especially as you're first working with these, the check is a good idea. So the derivative of capital F prime, 4 gets carried along as a multiple. Derivative of tan inverse is 1 over 1 plus u squared. The 1 over natural log of 3 carries along as a constant multiple. And then the derivative of 3 to the u is natural log of 3 times 3 to the u. So those natural logs reduce. And derivative of 7u is 7. And of course, a constant would go to 0. So again, we can always run that check and make sure we get what we started with. All right, let's just wrap up with one last example here. So number 7, let's take a look at lowercase f of x is equal to 1 plus tangent squared of x divided by 2. Now, a good first instinct would maybe be to split this into 2 different terms. We've done that before with these quotients. The problem here is going to be if I do that, and again, nothing wrong with thinking about that, I'm still going to be stuck because I don't know what the antiderivative of tangent squared is. So this is the one that I don't know its antiderivative. So we don't know a function whose derivative is equal to tangent squared. Excuse me. So not a bad effort, and we could, at this point, we could continue with this form, or we can go back to kind of the first original form, and what we really need to focus then on is this 1 plus tangent squared, or the tangent squared. So hopefully you can kind of recall here that you have some forms of, so let's just say, oops, sorry. So let's recall that, and whenever I learned the Pythagorean identities, I always just kind of learned the first one, like sine squared plus cosine squared was equal to 1. And I knew that there was others out there about tangent squared and cosecant squared and all that, but I I didn't really memorize them, at least at first. I would just think about how I get to them if I divide through by. So think about dividing everything through by cosine squared on both sides. Sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared. So what I really want you to remember, of course, is that 1 plus tangent squared is equal to, so recall that 1 plus tangent squared is equal to secant squared. So for us, we can actually replace, if we look back at the original function, we can replace this entire 1 plus tangent squared. That can actually be replaced then with secant squared. So our original function here, so f of x is equal to 1/2, just kind of that dividing by 2, secant squared of x. You also could have, it would have been more work, you could have subtracted 1, like right here, and thought of tangent squared as being secant squared minus 1, and then kept going with what you had here with the tangent squared. Just would have been a little bit more work here. So I'm just going to erase this. It wasn't a bad initial effort, it just didn't get us anywhere, and so we get to a point that this is hopefully what we remember. And so just with a little bit of trig there, we now take our antiderivative. We're ready to do that. So capital F of x is equal to 1/2 gets carried along as a constant multiple, and the function you learned whose derivative was secant squared, that was tangent of x. And again, always plus your arbitrary constant. All right, so there's a good mix of some of your basic antiderivative examples.